IL represents the lot rotor current, while IN stands for the nominal current. To determine the approximate load of the motor, we need to utilize the provided IL and IN values. Since the actual running current is not provided, we can use an approximation method. The formula to estimate the motor load is load equals the quantity IL minus IN divided by 2. By substituting the given values, that is, IL equals 156 amps and IN equals 48 amps, into the formula, we get load equals the quantity 156 amps minus 48 amps divided by 2. This simplifies to load equals 108 amps divided by 2, resulting in a load of 54 amps. Therefore, based on this approximation, the estimated load of the motor is 54 amps. It's important to understand the significance of both locked rotor current and nominal current. Locked rotor current, often abbreviated as LRA or IL, refers to the maximum current drawn by a motor when it is initially energized but the rotor is not yet turning. This condition occurs instantaneously at startup. The locked rotor current is significantly higher than the motor's normal full load running current. This high current draw is due to the motor acting essentially as a short circuit until the rotor begins to rotate and generate a counter-electromotive force, or backvolts, which opposes the applied voltage and limits the current flow. The magnitude of the locked rotor current is a crucial factor in determining the appropriate size of circuit breakers, fuses, and other overcurrent protection devices required to protect the motor and the branch circuit feeding it. Overcurrent protection must be capable of withstanding the inrush of locked rotor current without nuisance tripping, while still providing adequate protection against sustained overloads or short circuits. The locked rotor current is also a consideration in determining the voltage drop in the electrical system during motor starting. The high current draw can cause a temporary voltage sag, which may affect the operation of other equipment connected to the same electrical system. It is often necessary to use reduced voltage starting methods such as autotransformers, reactors, or part winding starters to limit the locked rotor current and minimize voltage drop during startup, especially for large motors. Nominal current, often denoted as IN or sometimes full load amps FLA, represents the current the motor draws when operating at its rated horsepower and voltage under full load conditions. This value is a key parameter for determining the appropriate conductor size for the motor's branch circuit, as well as for setting the overload protection. The National Electrical Code, NEC, specifies that the conductor ampacity must be at least 125% of the motor's full load current. This 125% factor accounts for the possibility of the motor operating continuously at its rated load. Overload protection devices, such as thermal overloads or electronic motor protection relays, are designed to protect the motor from overheating due to sustained overcurrent conditions. These devices are typically set to trip at a current level slightly above the motor's nominal current. Full load current is also used to calculate the motor's power factor and efficiency. Power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. A low power factor indicates a less efficient use of electrical power. Motor efficiency is the ratio of the mechanical power output to the electrical power input. A higher efficiency indicates a greater conversion of electrical energy into useful mechanical work. The approximation formula provided, load equals quantity IL minus IN divided by 2, offers a simplified method for estimating the actual load on the motor in the absence of direct current measurement. This approximation assumes that the actual running current falls somewhere between the nominal current and the locked rotor current, and that the load is proportional to the current draw. This is a rough estimate, and the actual load on the motor may vary depending on several factors, including the type of load, the operating conditions, and the motor's efficiency. It's important to note that this calculation is only an approximation and should not be used as a substitute for direct current measurement with an ammeter or clamp-on ammeter. Direct measurement provides a more accurate assessment of the motor's load and operating conditions. Now, let's delve into some related concepts and considerations when dealing with motor nameplate data. Motor service factor is an important rating found on the nameplate. The service factor indicates the amount of overload a motor can handle for a short period of time without causing damage. For example, a motor with a service factor of 1.15 can safely handle a 15% overload. However, operating a motor continuously above its rated horsepower will shorten its lifespan. Another important nameplate rating is the motor's insulation class. The insulation class indicates the maximum operating temperature that the motor's insulation can withstand. Common insulation classes include Class A, Class B, Class F, and Class H, each with a different temperature rating. Operating a motor above its insulation class temperature will cause the insulation to degrade, leading to premature motor failure. Motor enclosure type is another crucial factor to consider. The enclosure protects the motor from environmental conditions such as dust, moisture, and corrosive substances. Common enclosure types include open drip-proof, totally enclosed fan-cooled, and explosion-proof, each designed for specific applications. Open drip-proof (ODP) enclosures are suitable for clean, dry indoor environments. Totally enclosed fan-cooled TEC enclosures are suitable for more demanding environments where dust and moisture are present. Explosion-proof enclosures are designed for hazardous locations where flammable gases or vapors may be present. Motor horsepower (HP) is a measure of the mechanical power the motor can deliver. It is related to the motor's torque, which is the rotational force the motor produces, and speed, which is measured in revolutions per minute (RPM). The relationship between horsepower, torque, and speed is given by the formula horsepower equals torque times speed divided by 5,252, where torque is measured in pound-feet and speed is measured in RPM. Motor voltage and frequency are also important nameplate ratings. The voltage rating indicates the voltage at which the motor is designed to operate. Common voltage ratings include 120 volts, 208 volts, 230 volts, 460 volts, and 575 volts. The frequency rating indicates the frequency of the alternating current power supply, typically 60 Hz in North America. Operating a motor at the wrong voltage or frequency can cause damage to the motor. Motor efficiency is a measure of how well the motor converts electrical energy into mechanical energy. High-efficiency motors are designed to reduce energy consumption and operating costs. Motor power factor is a measure of how effectively the motor uses electrical power. A high power factor indicates a more efficient use of electrical power. Motor frame size is a standardized dimension that defines the motor's physical size and mounting dimensions. The National Electrical Manufacturers Association (NAME) publishes standards for motor frame sizes. Understanding motor nameplate data is essential for selecting, installing, and maintaining electric motors. By carefully reviewing the nameplate information, you can ensure that the motor is properly matched to the application and that it is operated within its safe operating limits. In addition to the nameplate data, it is also important to consider the motor's application and operating conditions when selecting and maintaining electric motors. Factors such as the type of load, the duty cycle, the ambient temperature, and the presence of corrosive substances can all affect the motor's performance and lifespan. Proper motor maintenance, including regular lubrication, cleaning, and inspection, is essential for ensuring reliable motor operation and preventing premature motor failure. Now let's consider some practical examples. Suppose you have a motor with a nameplate that indicates IL equals 200 amps and IN equals 60 amps. Using the approximation formula, we can estimate the motor load as follows: load equals quantity 200 amps minus 60 amps divided by 2, which equals 140 amps divided by 2, which equals 70 amps. Therefore, the approximate load of this motor is 70 amps. In another example, consider a motor with IL equals 120 amps and IN equals 40 amps. Applying the formula, we get load equals quantity 120 amps minus 40 amps divided by 2, which equals 80 amps divided by 2, which equals 40 amps. In this case, the estimated motor load is 40 amps. These examples illustrate how the approximation formula can be used to quickly estimate the motor load using the IL and IN values from the motor nameplate. However, remember that this is just an approximation, and direct current measurement is always recommended for more accurate assessment. When working with electric motors, always follow safe electrical practices. To energize the circuit before working on any electrical components. Use appropriate personal protective equipment, PPE, such as safety glasses, gloves, and insulated tools. If you are not qualified to work on electrical equipment, consult a licensed electrician. Understanding the relationship between rotor current, nominal current, and motor load is crucial for ensuring safe and efficient motor operation. By properly interpreting motor nameplate data and applying appropriate calculation methods, you can make informed decisions about motor selection, installation, and maintenance. Furthermore, understanding motor nameplate data is not only beneficial for practical applications but also for troubleshooting motor issues. For instance, if a motor is consistently drawing more current than its nominal current, it could indicate an overload condition, a mechanical problem, or a fault in the motor windings. Similarly, if the motor is drawing significantly less current than its nominal current, it could indicate an underload condition, a problem with the driven equipment, or a loss of one of the phases in a three-phase motor. By monitoring the motor's current draw and comparing it to the nameplate data, you can identify potential problems early and take corrective action before they lead to more serious issues. Additionally, motor nameplate data is essential for selecting the appropriate motor starter and overload protection devices. The motor starter is responsible for safely starting and stopping the motor, while the overload protection devices protect the motor from overheating due to sustained overcurrent conditions. The size and type of motor starter and overload protection devices must be carefully selected based on the motor's voltage, current, and horsepower ratings. Using undersized or incorrectly selected motor starters or overload protection devices can lead to motor damage, equipment failure, and even electrical hazards. In summary, understanding motor nameplate data, including IL and IN, is a fundamental skill for anyone working with electric motors. By knowing how to interpret this data and apply appropriate calculation methods, you can ensure safe, efficient, and reliable motor operation. Remember to always prioritize safety when working with electrical equipment and to consult a qualified electrician if you have any questions or concerns. Let's explore some additional aspects related to motor load and efficiency. The actual load on a motor can vary depending on several factors, including the type of driven equipment, the operating conditions, and the system efficiency. For example, a motor driving a pump may experience varying loads depending on the flow rate and pressure of the fluid being pumped. A motor driving a fan may experience varying loads depending on the airflow and static pressure. It is important to consider these factors when estimating the motor load and selecting the appropriate motor size. Operating a motor at less than its rated load can reduce its efficiency and increase energy consumption. This is because motors are typically designed to operate most efficiently at or near their rated load. When a motor is operated at a light load, it experiences increased losses due to factors such as friction, windage, and core losses. As a result, the motor's overall efficiency decreases and more energy is wasted. To improve energy efficiency, it is often recommended to use appropriately sized motors for the application. This may involve replacing an oversized motor with a smaller, more efficient motor. Another factor that can affect motor efficiency is voltage imbalance. Voltage imbalance occurs when the voltages and the three phases of a three-phase power system are not equal. Voltage imbalance can cause increased current draw, overheating, and reduced motor efficiency. To minimize voltage imbalance, it is important to ensure that the electrical system is properly balanced and that all connections are tight and clean. Harmonic distortion can also affect motor efficiency. Harmonic distortion is the presence of non-sinusoidal waveforms in the electrical system. Harmonic distortion can cause increased current draw, overheating, and reduced motor efficiency. To minimize harmonic distortion, it is important to use appropriate filtering and mitigation techniques. Finally, proper motor maintenance is essential for maintaining motor efficiency. Regular lubrication, cleaning, and inspection can help to prevent motor problems and ensure that the motor is operating at its peak efficiency. In addition to these factors, it is also important to consider the motor's starting characteristics. As mentioned earlier, motors draw high inrush current during startup, which can cause voltage dips and stress on the electrical system. To mitigate these effects, various motor starting methods can be used, such as reduced voltage starters, soft starters, and variable frequency drives. Reduced voltage starters limit the voltage applied to the motor during startup, reducing the inrush current. Soft starters gradually increase the voltage applied to the motor during startup, providing smoother acceleration and reducing mechanical stress. Variable frequency drives, VFDs, allow the motor speed and torque to be controlled electronically, providing precise control and energy savings. By carefully considering the motor's starting characteristics and selecting the appropriate starting method, you can minimize the impact on the electrical system and improve overall system efficiency. Furthermore, the location where the motor is installed plays a significant role in its longevity and performance. Motors operating in harsh environments with high temperatures, excessive dust, or corrosive substances require special considerations. High-temperature environments can degrade the motor's insulation, reducing its lifespan. In such cases, it is essential to select motors with appropriate insulation classes and cooling methods. Dusty environments can clog the motor's ventilation system, leading to overheating. In these situations, totally enclosed, fan-cooled TEFC motors are often preferred. Corrosive environments can damage the motor's windings and other components. In such cases, motors with special coatings or enclosures may be necessary. In addition to environmental factors, the motor's mounting and alignment are also critical. Improper mounting can cause excessive vibration, which can lead to bearing failure and other mechanical problems. Misalignment between the motor and the driven equipment can also cause excessive vibration and stress on the motor's bearings and couplings. Regular inspections and maintenance of the motor's mounting and alignment can help to prevent these problems. In conclusion, a thorough understanding of motor nameplate data, load characteristics, efficiency factors, sorting methods, environmental considerations, and maintenance practices is essential for ensuring safe, efficient, and reliable motor operation. By paying attention to these details, you can maximize the motor's performance, extend its lifespan, and minimize energy consumption.